Okay, we'll take a simple example. For a unity feedback system, g of s is equal to k divided by s plus 4, s plus 2. Sketch the rough nature of the root locus, showing all details on it. Comment on the stability of the system. So the step 1 is, that is as far as the rule number 1 goes, is try to find the number of poles. Yes, so we have here number of poles. Here are 3, 1, 2 and 3. So that is s equal to 0, s equal to minus 2 and minus 4. So number of poles is equal to 3 and number of zeros are equal to 0. So the total number of branches will be equal to number of poles. So that is what we have is 3, and the number of branches approaching to infinity will be equal to p minus z, which will be equal to 3. So we have here we have just simple plotted uh, uh, the poles and zeros here. So you can see here it is we have 0, minus 2 and minus 4. So once the pole 0 plot has been done, so we have to check for its existence of root locus. So how do we check it? So as we had discussed earlier, yes, we'll check it between minus 2 and 0. So check it here. So I'm checking out here. Yes, so from this point I can see there is only one pole. So what will happen? So the count will be here, then odd value. So as it is an odd value, then I can say it is that, so there is a root locus existing. Yes, so let's take to the next point here. If I take it in between minus 4 and minus 2, so if I take it here now, so if I check it from this point, so there I have 1 and 2 here, and one is at minus 2 and another is at 0. So hence I am having how many? It will be 2 now. So as 2 will be an even number, so I can just say that, so this part is not on the root locus. So I can write it here as NRL, not root locus. So further, if you move to this value point, so once again it will be a odd value, 1, 2 and 3 here. So the sum of all these poles and zeros will be 3. So as it is an odd value, hence I can say that as it's a root locus is existing on there. Okay, so further, so as we have 3 branches approaching to infinity, so does we will be having 3 asymptotes which are required, which will be moving to infinity. So we have to find the angles of the 3 asymptotes. So first we know that is theta equal to 2q plus 1 plus 1 bracket 180 degree mine divided by p minus z. So we have here q is equal to 0, 1, 2. So go on substituting with all those 0, 1, 2 value. So first instance we will be getting 60. Then we have next, if we substitute q equal to 1, I'll be getting 180. Theta 3 will be 2 into 2 multiplied by 1, which will be 1 to 180 divided by 3. So that turns out to be 300. So once the asymptotes have been angle of asymptotes have been found out, then we have to move on for centroid. So how do we find out the centroid here? So sigma, we have it as summation of the real values of the poles, yes, real part of the poles, minus summation of real parts of the zeros. So we'll check out with the real part of poles we have. So what do we have? Do we have a real parts of poles here? So these are the values what we are having here. Yes, 0, minus 2 and minus 4. So we'll write the same way, 0, minus 2 and minus 4. Do we have any minus real parts of poles, zeros? So do we have anything as such? No, we don't have any zeros, real parts of zeros here. So hence we have left it as it is. So as the real values are 0, minus 2 and minus 4, so we have written them. Divided by p minus z will be 3. So p minus z is 3, so hence the value turns out to be minus 6 divided by 3, so that is equal to minus 2. So once this is round write down, we have got down the centroid value. So we'll plot once again with these. So we have taken minus 2 as this here, minus 2 as you can note out here. Yes, so minus 2. With this they are moving the first asymptote with the theta 1 as the 60 degree, it is moving this direction, and another at 180 degree, it is theta 2, it is moving in this direction along the y-axis. Then we have along the negative x-axis, and the other one is what we have here is the theta 3, which is moving with the 300 degree angle. Okay, so these three branches will be approaching to the infinity. So further, if you have, now we have to find the breakaway points. So breakaway point has to be found out, that is as per reference rule number 6. So we have to find the breakaway point. So how did we find the breakaway points? That is whether it is between, we have to check here first. Here we have to check whether the breakaway points are there or not. So in the second step itself, we have to find out whether the breakaway points are existing or not. So what is that? Between any two adjacent poles or between any adjacent zeros, okay, there should be an existence of root locus, then only there exists a minimum breakaway point. So what is happening? So ಇಲ್ಲಿ already ಇಲ್ಲಿ ಎರಡು adjacent ಪೋಲ್ಗಳು ಇದ್ದಾವೆ. ಸೊ ಅದರ ನಡುವರ್ಗೆ ಏನು ನಮಗೆ ಏನು ವ್ಯಾಲ್ಯೂ ಇದೆ, ಸೊ ದಟ್ ಈಸ್ ಅ ರೂಟ್ ಲೋಕಸ್ ವ್ಯಾಲ್ಯೂ. ಹೆನ್ಸ್ we are I can say that there is minimum one breakaway point. So have a one breakaway point here. I don't have here. Yes, these are non adjacent poles, but yet we don't have a, because there is a not existence of root locus, we cannot put one more breakaway. So in a similar way, so I can say that finally there is one breakaway point. So that's why I have to find the breakaway point value here. So how do we get now? So breakaway point 1 plus g of s into h of s. Next equal to 0. Substitute. We have taken that. Take all the values in terms of k. So first equate this here, and I can get the values in terms of k. So once this k is been taken, so differentiate with respect to x, s, and equate it to 0. So once I have already have already taken the differentiation here, and I have equated it to 0. Further, its roots are being derived. So take out the roots. 3s square plus 12s plus 8 is equal to 0. We can find out the roots as, so once this I can make out here the roots are minus 8, minus 0.845 and minus 3.15. So we have to check for the existence of these things. How do we check it? So substitute these values once again in equation 1, that is what we have for k. Okay, so if we get the positive value, then we can say that it is a valid breakaway point. So I'll substitute the first minus 0.845. so I am getting here, yes, I am getting a k value to be a plus 3.079. yes, then it will be a valid breakaway point. So similarly, if I substitute minus 3.15, so which I am getting it to be as a minus 3.079. so hence I cannot say that this is a valid breakaway point. So there is only one valid breakaway point which I am able to see here, that is s equal to minus 0.845. yes. So once I have got this valid breakaway point, now I have to go for finding out the intersection point with the imaginary axis. Okay, so that is we have this characteristic equation. Yes, previous equation we have taken. So the same equation is being taken here, s cube plus 6s square plus 8s plus k. So take out the roots array, write it here, write their coefficients 1, 8, then we have 6, k, k. So perform it. So by performing the roots method, you can write it here 48 minus 4 divided by 6. The other one is 0. Then we have divided by k. So once it is done, so we must understand this all in order to, for the stability of a system, we must understand the k value should be greater than or equal to 0. If it's a marginal value, if you are taking out, this value has to be 0. Okay, so we have to make sure that we have to the other this one row should become 0. So we have here, so k marginal, I am trying to take it out, so this value has to be 48. Okay, so if I take k marginal to be 48, then which makes row s1 to be 0. So this, if I take it this value, you can see here, so 48, so this should be not 4, 48 minus 4 is being written here, this is not minus 4, this should be minus k. Okay, so fine. So what is exactly here is so if this k becomes 48, so this value turns out to be 0. So then I can say this is a k marginal value. So hence once we know that the k marginal is value is a 48, so the above this equation, above this s1, we have s2 value. This equation we have to consider and rewrite the equation. So that is augmented equation we have to write, that is we are taking it as a of s is equal to 6s square plus k. So we have k margin to be equal to 48, then substitute the same value. Okay, 6s square plus 48 is equal to 0. So s square equal to minus 8, s equal to plus or minus j of root 8. So we have plus or minus j 2.88. So these are the values to which it is intersecting. Okay, so the intersection of root locus with imaginary axis is at plus or minus j 2.828, and the corresponding value for is of the k margin will be 48. Now we can say that as there are no complex conjugate poles, yes, if you have taken already the poles values, so we didn't find any conjugate poles there, hence there are no need to do the 7th and 8th step, that is need not to find the angle of departure and angle of arrival, so hence that part can be left out. So 8th step is complete the root locus. So 9 then this is what is the complete root locus and 9th step will be prediction of the stability. Yes, so first we will try to plot it first how it is. So we can see here, yes, 0 here we have, and minus 2 is there, and I have taken a centroid to be is at minus 2, and then I have to draw a breakaway point. This is my centroid, so from which this one is 60 degree what is moving out, and the other is 180, and theta 3 is 300. And how are these breakaway points are moving out is, so they are moving in parallel. You can see just here where it is intersecting, it is intersecting at j.28. so what is that, it is plus j 2.82, so it is minus here minus 0.282. okay, so this is where it is intersecting, so this should move in parallel to this one, so it should go in this way. Okay, should go in the parallel way. Okay, this is how it is moving, you can see here, so this is should go in this way. Okay, so this is how we, and these values are taken when k marginal to b is to be 48. So how do we predict the stability here is for k to be greater than 0 and less than 48, all the roots in the left plane S planar system is absolutely stable. for k margin to be plus 48, a pair of dominant roots on the imaginary axis with remaining root in the left half. So the system is marginally stable, oscillating at 2.82 radians per second. For k to be less than 48 and greater than, and for k greater than 48 and less than infinity, the dominant roots are located in the right half of S plane, and hence the system remains to be unstable. Yes, so we can say here is that, so the beyond this value, okay, beyond this value, okay, the value turns out to be, that is beyond the k margin value greater than 48, the value turns out to be unstable, and within these values between less than 48, the system remains to be stable. So this is how we predict the stability of the system using the Rootlocus. We'll take one more simple example and we'll try to understand. Yeah. Let's sketch the Rootlocus of the system having g of s equal to k divided by s into s square plus 2s plus 2. So we have number of poles here. How many we have? S is order of 3 here, so 1 and 2, so definitely will be having p equal to 3, and z we have nil here, so we have 0 equal to 0. So number of branches will be equal to number of poles, so that is 3. So p minus z will be the that is will be equal to 3. So these will be the number of branches that will be approaching to the infinity. Okay, so we'll try to find the roots now. So s is equal to 0, and the another one is s equal to minus 1 plus j, and the other one is minus 1 minus j. So yes, here we come across with the complex conjugates. Okay, so hence we have to perform the rule number 7 and 8. Okay, so here it will come. So we have to first predict the whether the existence of the Rootlocus. So first we'll plot it here. So take down, s is at 0 1, and s is at minus 1 plus j, minus 1 plus j, and minus 1 minus j. So with this we'll have to predict the existence of the Rootlocus. So suppose if I want to take it from here, okay, suppose if I want to take it from here, so if you take it at the right side, so have 1 2 and 3, so there are totally how many? So 3 sum of all the poles we have here is 3, as this will be a odd value, hence yes, I can say that this exists on the Rootlocus. So from from point here to here it will be on the Rootlocus, while beyond on the right hand side that will be a non Rootlocus. Yes, now we must also look for the breakaway points. We have to check whether there is any breakaway point or not. So what is the thing what we have for breakaway point is that, check it out here. We have anything we have a Rootlocus existing, but we don't have any adjacent poles. So as these all are both are on this side, so we don't have any adjacent poles. Okay, so hence there is no breakaway point exists here. So we don't have any adjacent poles here, so hence hence we can say that there is no breakaway point. Okay, okay, so adjacent, maybe these are there, but I cannot say these are complex conjugate values, so I cannot say that these are the adjacent ones. Okay, fine, so I cannot say that as a adjacent one. So fine, so as we have 3 branches moving to infinity, I can say that now we have to find the angle of asymptotes of 3 branches. So 3 asymptote angles has to be found out. So go ahead, we'll have to find 2q plus 1 divided by 180 minus p by z. So we have 0, 1, 2. So 180 divided by 3, 60, 180 and 300. So centroid we have equal to sigma equal to, we have RP, real part of poles minus real part of zeros divided by P minus Z. So we had a real part of poles. One pole is 0, minus 1, minus 1. So we have here, so we have real parts are 0, minus 1, minus 1, and the real part of 0 is not there, so it is 0. So total divided by 3. So the centroid will be minus 2 divided by 3. So hence it is minus 0.657. So hence we have to draw it one more time, that is draw it here, take the centroid as minus 6.67. So the asymptotes will be moving in this fashion. Yes, one is at 60, 180 and other at the 300. So now we have to find the breakaway point. So breakaway point 1 plus g of s, yes. So take it the value of k minus s3 cube. We have to do this process, minus s cube to s square. So differentiate this value and equate it to 0. We find these values as minus 0.6.7 plus or minus j. So now instead of substituting minus 0.67 j in expression for k, we can check the validity of these breakaway points using the angle addition, as we have angle addition method also. So we can do with that, that is minus 6.67 divided by 0.417. So take its angle now. So k divided by s plus 1 plus j, s plus 1 minus j. So at this point we will try to get its angle here. For this angle 1, and this for this value one more angle, that is substituting s equal to this value. So I have checked here, this is one angle we have got here, this is one, this is one. So yeah, I get some angle equal to 144.87 and 77.34 minus 58.04. So the value what you are turning out to be is minus 164.11. Yes, this is not an odd multiple of 180, hence the point is not on the root locus, hence there are no breakaway point existing for the system. This we have already as a prediction, we have already done it at the second step itself, that is, but still we have to do it for the clarity. So we have to check, we can say that there is no breakaway point existing for the system. Yes. So intersection with imaginary axis. So take the rows array 1 s cube plus 2s square plus 2s plus k. So we have 1, 2, then we have next one is 2s square 2 and k. Then we have further process 4 minus k divided by 2 equal to 0. So the k margins we have to find such a, we have to put a such a value that this row becomes 0. So if I put substitute k equal to 4, then my value would be 0. So what will happen? So my k marginal value will be plus 4. So now I have to take the above equation, or the above equation, that is what we have. A of s is equal to 2s square plus k, which is equal to 0. So this k we have to put it as k marginal value as k equal to 4. So that is what I have done here. 2s square plus 4 equal to 0. So we have s square equal to minus 2. So we have, therefore yes, I can say that plus or minus j of 1 plus 4.14. So this is what is the, this is where these values are intersecting at 1.414 value. Okay. So for these values we have to find the angle of departure and angle of arrival. So as there is no availability of zeros there, so we cannot, there is only we have to find out for the angle of departure. Angle of arrival is not needed here. So angle of departure is equal to, as a branch is departing at, we'll take the first value at -1 plus j. So we'll considering this value, we'll first calculate. So take it, I'm taking this value now. Okay, so this is, so we have to connect all those points and try to calculate the angles. This is 5p1 and this is 5p2. So 5p1 equal to 135. You can calculate it by your trigonometric functions. Then 5p2 equal to 90 degree. You can see that. So total 5p will be equal to 5p1 plus 5p2. Then we have 5z, which is not there, so it is equal to 0. So therefore 5 is equal to, we have summation of 5p minus 5z, which is equal to 225 minus 0, which is equal to 225. Then we have 5d equal to 180 minus 5. Though this is 5, we have got the value as 225. So 180 minus 225 is equal to minus 45. So this is minus 45 for the angle of departure for minus 1 plus j. So in a similar way, if you try to calculate for minus 1 minus j, the 5d value will be plus 45. So usually the what exactly happens will be, it will be an opposite angle. So because these are complex conjugate values, so definitely the angle will be the quite opposite value. So we have here one is minus 45 and the another plus 45. So with this we have to draw the final drawing, final root locus drawing. So you can see here, that is, yes, I can make it out here. So I have drawn the pole here 0, and the other one is at where, one is at minus 1 plus j, minus 1 minus j. So your asymptotes are moving in this direction. One is at 60 degree, 180, and the other one is at, we have 300. But these breakaway points are not there, but but how exactly they are moving will be here. Okay, so they are intersecting at weight value 1.141. so that is what we have derived. So this one will, another will be 1.1414. okay, then further we have to make a bit of angle here, that is, it should be such a way that it should be making some angle of 45 degree. So takes in that 45 degree angle. Okay, then make just an angle so that it will resemble 45 degree. So this is minus 45 degree, we can take it out here, and this is plus 45. So with that as a reference, it will move it till a 45 degree, and then further it will move to the, as it is with the asymptote what we have it here. Okay, so take it 45 degree, then move it as it's along with the asymptote. So this is how it does move. So the prediction is that as the k margin is 4, so if it moves beyond the k margin value plus more than 4, so the value turns out to be unstable. Okay, so that is for k, greater than 0 and less than 4, all the roots in the left f-spline is absolutely stable. But at the k plus 4, the all the are marginally stable, and which is oscillating with 1.414 radians per second. And k value greater than 4, then the all the dominants will be, roots will be in the right half of s-plane, and hence the system becomes unstable. Okay, it's a very simple writing of procedure. So these are how the examples are generally done. There are a lot many examples being given in your textbooks. Do refer them. So these are very simple sort of examples. If you don't have anything, if you don't understand, you can ping me up. Okay. I will try to resolve the issues. Fine. The other part is uh, the next one more concept that has to be understood, that is what would how would it affect uh, by the addition of poles and zeros to the system. So we'll take the first one, the addition of pole. So what happens if I go on adding the pole? So let me take as a simple condition here, g of s into h of s I have taken. So k divided by s plus 2 I have taken. It's root locus, yes, s is 0, minus 2, 1 breakaway point exists here, we can see that. Then what do I do? Next case, I add one more pole here. We have I'm adding one more pole, that is at s equal to minus 4. I've added here minus 4. So what exactly happens? So this tends moving this side, okay, so there will be a k existence. So the marginal value, it turns out to be at some value here, it is intersecting here. So beyond this k margin value, it's your system tends to be unstable. So what will exactly happen? So if I add one more pole, so what is happening? So this whole thing is once again getting shifted, okay, your centroid is getting shifted inside, yes, is it not? So this will be your new breakaway point, we can see here. So your breakaway point is getting shifted inside. So what is happening? Further the system is tending to instability. So if you go on adding the number of poles, the system tends to become unstable, okay. So this is what is the outline. So we can be summarize that the effect of addition of open loop poles can be summarized as root locus shift towards the imaginary axis. Yes, the system stability relatively decreases, the system becomes more oscillatory in nature, the range of operating values of k for stability system decreases. Yes, so this is what is. So as and we go on adding the number of poles into the system, so does the system tends to become unstable. So that is what we can understand from this. Yes, what would happen now if addition of there is a 0? We can take, I have taken the same system here, h of s equal to, we have k divided by s plus 2. Further I add s minus, I have added one 0 here, s plus 4. So what is happening? So it is, you can see that it is revolving in between, yes. So you can see that is the breakaway points are just revolving here between minus 4 and minus 2. So if you further go on adding number of 0, if I go for s plus 6, so further this breakaway point is further it is moving to your left side, okay. So new breakaway point is, it is moving further to the left, that is of s plane. So what is happening? So it is still it is moving towards the stability. So as and it moves towards the left of s plane, so definitely it will, the stability of the system does increase, okay. So we'll try to summarize the things. Yes, the root locus shifts to the left away from the imaginary axis. Relatively the stability of the system increases, the system becomes less oscillatory, and the range for operating values of k for the system stability increases. Yes, so one must understand that as we go on adding the number of zeros, so does the system goes to the stability. So this is all what is regarding the root locus. If any doubts, we can be pinged, and the issues may be addressed, okay. So with this we'll wind up the root locus session. Thank you.